So here we go. Let's do a quick review of complex numbers. Quick review of complex numbers. You know quite a bit about these. Matter of fact, I bet some of you could even tell me what a complex number is. What the heck's a complex number? Complex number. A number that isn't simple? I know you've seen it before. You might not just remember what it's called.
Pi.
Did you say pi? I, yeah. I. So something like this. A plus B I. That's a complex number. That's a true complex number. Matter of fact, all of our numbers, known numbers in our number system are considered complex numbers. This is a true complex number because it has what's called a real part right here. And then this is called the imaginary part. A real part plus an imaginary part forms a complex number. I don't think this was part of the Algebra 2 curriculum, but you can graph complex numbers on what's called a complex plane. Some of you might have seen this, but for most of you I think this will be something new. It's pretty easy. A complex plane is a rectangular coordinate system, kind of like the Cartesian XY plane. It has a vertical axis and it has a horizontal axis, but it's not an X and a Y axis. This axis right here is called the real axis. That's the horizontal one. The vertical axis is called the imaginary axis. So to graph or to plot a complex number on the complex plane, it has a rectangular coordinate system. The real part is the horizontal component, the imaginary part is the vertical component. So for example, if we wanted to plot the number 3 minus 2i, the 3 is the real part of this complex number, so that goes on the real axis, 3 units over. And then the negative 2i, that's the imaginary part, that goes on the imaginary axis, so it's negative 2 units down on the imaginary axis. So this point right here represents the complex number 3 minus 2i. So where do you think we're going with this? If you wrote down the objectives, polar form of complex numbers, consider what we did last time, or last time. If we can locate a point on a rectangular coordinate system, couldn't we also locate that same point on a polar axis system? What would we need to know to describe the location of this point using polar coordinates? We need to know two things. We need to know the distance from the pole to the point, and we need to know the angle that it makes. So that's exactly what we're doing today. We're going to take complex numbers like this and rewrite them in what's called their polar form, or other textbooks call them their trigonometric form. Okay? So that's where we're going with this. This is really all I wanted to do with that first objective, is to introduce the complex plane, show you how to plot a few points. Okay? Other things you might need to quickly recall, just as I'm thinking about it. How would you, what are you going to have to know? How would you do this? How would you perform that operation? FOIL? If this were multiply, then yeah, we would have to FOIL. And we're going to do that here in a second, but if it's just add, just adding like terms, the real parts add together, so that's going to be negative 4, and then the complex or the imaginary parts add together. You've got to be careful with keeping track of your minuses and your negatives and all that stuff. But 6i plus negative 2i, that's how you add complex numbers. What if we did the same thing with multiply? 4 plus 6i, negative 8 minus 2i. What about here? Here we would FOIL. So you go here, here. Oh man. Negative 32 minus 8i minus 48i. Now what? We FOILed. I squared is really negative 1. Negative 1 times negative 12 is 12. You're right. So that becomes a positive 12. When combined with negative 32, makes negative 20 minus 56i. So all of this stuff I think you guys learned how to do last year in Algebra 2. What we're going to see is that many of these operations are much easier to do using this idea of converting them to polar form. For example, could you imagine how to do this problem here? We're not going to do it because it would take forever, but what if I asked you to do 4 plus 6i and raise that to the 4th power? How would you do that problem?
That triangle thing.
Pascal's triangle?
Pascal's triangle.
Yeah. But if you're not familiar with Pascal's triangle or binomial expansion, wouldn't you have to write 4 of these parentheses and do the FOIL method, an extension of the FOIL method, and that would take some sweet time, right? If it's in this form, doing this operation is pretty tricky. If we can transfer this to polar form, this operation right here is actually very simple to do. So that's the reason that we're learning what we're learning today. It's not just nice to go back and forth from one form to the other. It's actually very helpful in performing these operations. So anyway, that's where we're headed with this. Let's go into that second objective. Polar form of complex numbers. It's almost identical to what we did in that last lesson, transferring from rectangular form to polar form. So let's take a look. You don't have to redraw it if you drew it already. If not, draw that complex number that we already drew. 3 units on the real axis, 2 units down on the imaginary axis. So like you guys mentioned earlier, we need to know the distance. Now rather than calling this r, they now give this the variable z. And not that it's super important, but in case you're wondering, or if you read this in your textbook somewhere, that's called the modulus. But that's the distance from the origin to the point. Now, I know you guys are clever enough to figure this out. Think about how we did this on that quiz I just had you correct. When we're going from rectangular form to polar form, r equals the square root of x squared plus y squared. It's almost the exact same thing here. What's the formula going to be? Z equals what? Think about what a complex number is. A plus bi.
Real number squared. 9.
Well, not, just think in general, not in terms of actual here.
A squared minus b squared.
Yes. But what do you put the I in?
Do we need, okay. You guys are really dang close. Do we need, my question is, do we need the I component?
No, so it would be a squared minus b squared. B squared is all.
What?
Would you put I?
We'd have to have a square root.
Yeah, the square root of a squared minus b squared. Because the I squared is negative 1. Multiply that to b squared.
I see. Okay, I see why you have a minus line in there. We actually can keep it as a plus because if we just think about a triangle, then all we need really are the components without the I. This is positive 3. This is negative 2. So we just need the A and the B component without the I. So this is just going to be the square root of A squared plus B squared. So in particular now, we want to use our example of a distance of 3 to the right and then going down -2. What would the modulus be for this particular one? Z equals
9.
square root of 9 plus 4. Gesundheit. So Z equals square root
13.
of 13. That would be the modulus for this particular complex number. Nope. So we're just talking about distances here now. We went a distance of 3 to the right and a distance of down 2, so that's -2. Oh, before I forget, I don't want to not mention this. Put a little star here. This is also referred, oh boy, did I spell that right? Referred, probably, to as the absolute value. Of the complex number. So the modulus is also referred to as the absolute value. The absolute value of a number is the distance from 0 on a number line. So with complex numbers, this is the distance from the origin of the complex plane. What else do we need to know? We know the modulus. What else do we need to know? Yeah, we need to know the angle. Right there. That's called the argument. Theta is called the argument. Of the complex number. So it's just the exact same. Instead of the tangent of theta equals y over x, tangent of theta can equal what over what? Do you think? Remember, a complex number is a plus bi, where a is the horizontal component, b would be referred to as the vertical component. B over a. Oh no. Go back up a second. Go back up to this picture here. Polar form and complex. Yeah. Oh god. Alright. Get out your correction fluid. Shoot. It's still called the modulus. But they do actually call it R. Change all of these to R, R, R. R is the distance. Z, R is equal to the absolute value of Z. That's the distance. Make that correction. Okay. So let's see what a complex number looks like in polar form. Complex number, write this down. A complex number comes in the form a plus bi, but in polar form, it looks like this.
you please send Jacob Wilkins to the counseling office?
Yeah.
Thank you.
Oh, there he is. Yep. Okay, just real quick in case you're wondering where this even comes from. Draw a quick sketch. So we have this complex number a plus bi. The distance from the origin to that complex number we're going to call r. And then we have this right triangle. Now, we did a little bit of this last time, but you might have forgotten, so I'll just help you remember. If this were a rectangular coordinate system, wouldn't this be called x and this would be called y? But isn't x just r cosine theta? Didn't remember this from last time? And what is y? R sine theta. Is this looking a little familiar? Now, to describe the location of a complex number, you have to combine the real part with the imaginary part. That's why it's a plus bi. But if the horizontal component is just r cosine theta and the vertical component is r sine theta, then in polar form this is going to be r cosine theta plus, and the vertical component has to have that I combined to it, so it's I sine, or sorry, I r sine theta. And if you factor out an r from both of those, you get r times parenthesis cosine theta plus I sine theta. That's where that comes from in case we were wondering. Now, I'm not going to write it like this. It takes too much time. There's abbreviation. I don't know if our textbook uses it or not. Doesn't look like it, but I'm going to use it because other textbooks do. This is abbreviated to this. Feel free to use that abbreviation if you want. CIS. It's not a new trig function. It's just short for cosine plus I sine theta. So actually, we can write that over here. R CIS theta. So let's practice. Example 1. Write in polar form. Here's part A, 1 plus I. That's a number, complex number, in standard form. So what two things do we need to know in order to write this in polar form? We need to know r and theta. It's exactly like writing rectangular form and polar form. So r is equal to the square root of a squared plus b squared, and theta, well, rather tangent of theta is equal to b over a. So those are two things we got to do. Figure out the value of r, figure out the value of theta using these formulas. These are exactly the same formulas really as the ones from section 8.1. You got to be careful here though. What is b? B is really a 1. B is the coefficient of I, and there isn't one that appears there, but there's really a 1. So a equals 1, and b equals 1. 1 squared plus 1 squared is 2, so r equals square root of 2. Now tangent theta is b divided by a, that's 1 divided by 1, so the tangent of theta is equal to 1 not 90, no, you're close. 45. Yeah. So if you take the inverse tangent on both sides, you get theta is equal to inverse tangent of 1. If you type this into your calculator, it should give you that if it's in degree mode. Now, you need to listen very carefully to what I'm about to say, because very, very, very many students mess up on this. You need to consider your answer, or the angle you've gotten, and then you need to consider where that complex number is and make sure that this angle is in the correct quadrant. Where is 1 plus I? First quadrant. Right? Where is 45 degrees? First quadrant. The reason I'm telling you this is, what if I put negative 1 plus negative I? Where would that be? That would be in the third quadrant, but wouldn't we still have gotten the same answer for this? 45 degrees? So you'd have to make a little adjustment. What adjustment would you have to make? If the number had started with negative 1 minus I, what would you have to change to here? You have to add 180 degrees to put you in the third quadrant. That would change your angle. A lot of students forget that. Make sure you're always considering what angle you're getting here and what quadrant the complex number starts in.
How do you know what quadrant?
1 plus I, you go over 1 up 1. That's in quadrant 1. So we know r and theta, but now we need to really write this number in its true polar form. So in polar form, a complex number is r parenthesis cosine theta plus I sine theta. So this is going to be square root of 2 times cosine 45 plus I sine 45. You can leave it like that if you want. I would say it would be easier just to write it like this. Square root of 2 CIS 45. This is the complex number in polar form, or trig form. Other textbooks might call it trig form. Let's try another one. I know I'm going super quick, but there's a little bit more I want to get to before we're done. Here's, let's do negative 1 plus square root of 3 I. Negative 1 plus square root of 3i. Before you do anything, where the heck is this number? On the complex plane, where would it be? We'd be in quadrant 2. You go negative 1 to the left, and then up square root of 3. So yeah, it's in quadrant 2. So planning ahead, you should expect to get an angle between 90 degrees and 180 degrees when you're finding the argument of this. So anyway, r is equal to the square root of a squared plus b squared. Be careful on this one. Ooh, this one actually turns out pretty nice. What do we get for r? 2. Where the heck did 2 come from? You're right, it is 2. You have negative 1 squared plus square root of 3 squared. Negative 1 squared is 1. Square root of 3 squared is 3. 1 plus 3 is 4. Square root of 4 is 2. All right. Alright, tangent of theta is b over a. So it's square root of 3 over negative 1. Essentially, that's just negative square root of 3. So for you to type that into a calculator, it's going to give you a negative angle measure in the fourth quadrant somewhere. So you got to really be clever about where that angle would also be in the second quadrant. Here's what I'm talking about. So if you just type in inverse tangent of negative square root of 3, tells you it's negative 60 degrees. And it's true. Inverse tangent negative square root of 3 is negative 60 degrees, but negative 60 degrees is not the angle you're going to use because this is in the fourth quadrant. That's right here. So we need to find a corresponding angle in the second quadrant that has that same reference angle. Did you understand what I just said? We need to find an angle in the second quadrant that has this angle as a reference angle. So it would be 120. Okay? Yeah.
Doesn't matter if we go like which way we go.
What do you mean?
Because the reference angle would also get rid of.
Reference angles are always less than 90. They're always positive as well. So I know this angle is negative 60. That's the angle, but the reference angle here would be going this way. So the reference angle is 60 degrees. Does that make sense? So if we think about some angle here in the second quadrant, it has to be 120 degrees because that has the same reference angle of 60 degrees. So the angle we want is 120 degrees. You know what? Well, I don't want to confuse anybody. I don't really like what our textbook does with this. Most college textbooks, in case you're wondering, what most college textbooks do is they do this. The tangent of theta is the absolute value of b over a. Does that make a huge difference? It makes it positive, and that actually is kind of a big deal. Why is that such a big deal? If this is always going to be positive, then the inverse tangent of positive something is always going to give you an angle in which quadrant? Always. Always in the first quadrant. So you never have to worry about negative angles, and then you just use it as a reference angle for whatever angle you need. That's I don't really like what our book does here with that. But anyway, it is what it is. The theta that we need is 120 degrees. So in polar form, instead of negative 1 plus square root of 3i, it's going to be 2 CIS of 120 degrees. These could also be in radians. They don't always have to be in degrees. You can keep them in degrees if you want. Let's go the other way. Let's do example 2. What if they're already in polar form? And you got to go back. Change to standard form. Or complex number. Let's do 8 CIS 7 pi over 6. We can change this back to standard form. Now this is just an abbreviation. This is not a trig function. You can't evaluate CIS of 7 pi over 6. That doesn't exist. You have to expand this. What is CIS? Yeah, it's cosine plus I sine. So the first thing you got to do is expand this. This is going to be 8 parenthesis cosine 7 pi over 6 plus I sine 7 pi over 6. And those can be evaluated because those are actual trig functions. Cosine and sine are trig functions. And 7 pi over 6, I believe, is one of our nice angles on the unit circle. So get that out if you have it. And hey, look, it is. That angle on the unit circle. 7 pi over 6 is right there, 210 degrees. So the cosine of 7 pi over 6 is negative root 3 over 2. So this is going to be 8 negative root 3 over 2. And then the sine of 7 pi over 6 is negative 1/2, so that's going to be plus negative 1/2. Don't forget the I. Now what do we do with that 8? distributed to both terms, yep. Oh, everybody stop for just a second. Stop, I should have asked you this at the beginning. Before we finish this up, consider where we started. 7 pi over 6, 7 pi over 6. Where is that? 7 pi over 6. That's in the third quadrant, right? So we're talking about some kind of a complex number in the third quadrant. So when we end up with a complex number in standard form, A and B should both be negative to lead you to the third quadrant. Just keep that in mind. It looks like it's going to be true here. Both A and B are negative. So we're going to have negative 4 square root of 3 minus what? Negative 4 root 3 minus 4i. That would be the complex number in standard form.
Don't you do where the 7 pi equals this is right? To the quadrant?
Yeah, this is in the third quadrant because you're going to the left and then down. So, yep. Before I actually get to that third topic, Dommage's theorem, we have multiplication. Here we go. Multiplication and division. I already showed you an example of multiplication of complex numbers in standard form. You might not remember this, but dividing complex numbers wasn't really easy to do. For example, this one here, 3 minus 2i divided by 1 plus I. Do you remember how this was even done back in Algebra 2? You had to, yeah. What do you mean? You had to multiply the top and bottom by the conjugate of the denominator. Does this look familiar to anybody? So in standard form, dividing complex numbers is not the easiest. I mean, I guess this isn't too bad. It just takes a little bit of time. Really what this turns out to be is a glorified multiplication problem. But that's what you guys learned how to do back in Algebra 2. Dividing complex numbers in polar form is really easy. Same with multiplying complex numbers in polar form. So that's another reason that we learn this, is it helps these simple operations go a lot easier. So in polar form, let's say if Z1 equals R1 CIS theta 1. So there's our first complex number, Z1. And Z2 is R2 CIS theta 2. So there's the second complex number in polar form. Then Z1 times Z2 if you're multiplying two complex numbers in polar form, you multiply the moduli, or their distances, so it's R1 times R2 and then you add the arguments, so you add the two angle measures. That's how you multiply two complex numbers when they're in polar form. Much easier to do than using the FOIL method, or much quicker to do. Same thing about dividing. If you have Z1 divided by Z2, you divide the two R numbers and subtract the angle measures. Yeah.
We're gonna have to memorize this.
Yes. Yes, you are. do a quick example of this. Example 3. Let's say that Z1 is 2, say S pi fourths, Z2 is this little guy here. Just practice this theorem. So find the product of those two complex numbers and then find the quotient of those two complex numbers. Multiply them and divide them. Well, part A, not so terrible. To find the product of two complex numbers, you multiply the two R values of the two complex numbers. What do we get out of that? You multiply the two R values of each complex number. So we're going to get 2 times 5, which is, get your calculators out if you need to. 2 times 5 is 10. You multiply the two R values.
I was reading.
Okay, and then you add the two angle measures of each complex number. So we have to add pi fourths to pi thirds. Pi fourths plus pi thirds. You can't add them unless they have a common denominator. So this is going to be 3 pi twelfths plus 4 pi twelfths, which is 7 pi twelfths. So you guys, this is simple arithmetic here. And unless it specifies otherwise, unless it specifically says express your answer in standard form, you can just leave it in polar form like this, which is nice. So let's do the quotient. Z1 divided by Z2, according to the split-toe theorem with, well, formulas rather than theorems, you divide the two R values. Z1 divided by Z2, we're going to have to divide 2 by 5, so that's 2/5. And then according to this little formula, we take the difference of the two angle measures, so it's going to be pi fourths minus pi thirds. So what is that? Yep. So this is 2/5 CIS negative pi twelfths. And you can just leave it in polar form like that. You need to read the directions of your homework and on the exam. Here's what I mean by that. If these are the directions, which they might be, if the directions specifically say this, express in standard form, then you would not be done at this point. What would you have to do to each of these? You have to convert it back into the standard form of a complex number, which is exactly what we did in that last example, right? Where'd you go? Right here. So it's not that hard to do. It takes a few extra seconds. But you need to listen. You need to read your directions carefully. Okay. Let's try another one. Sample 4.
Can you even put the homework on?
Is that not on there?
Uh-uh.
Oh, okay. I did not know that. I'll put it on after class. Example 4. I'm gonna mix things up here a little bit. Let's say that Z1, same directions. Z1 is equal to square root of 2 minus 2i. Sorry, square root of 2 minus the square root of 2i. Yo!
Do you have some Theorem clippers?
And Z2 is equal to 1 minus I. Part A, I want you to find the product. Part B, I want you to find the quotient. Z1 divided by Z2. So what's the issue here? They're not really in polar form. Now, we could, I guess, leave them in this form and try to make our way through it using algebra and just using the FOIL method. But the intent of this problem is that you change both of these into their polar form and use those formulas, because it's much easier to do these operations when they're in polar form. So, we need to rewrite this Z1 in polar form.
Then do you have to convert it back into this?
Unless it says to. No, this one doesn't say to, so you can leave your answer in polar form. So for that first one in polar form, what is it going to be? We need to know those two things. We need to know R, and we need to know theta. Yeah, R is going to equal the square root of a squared plus b squared. Well, this one kind of turns out nice. Doesn't it? This turns out to be the square root of the square root of 2 squared plus the square root of 2 squared. Well, it's really negative square root of 2 squared, but when you square something, it comes out positive anyway, so it doesn't make a difference. What is this going to be? Square root of 4, which is 2. Well, that's super nice. And even Mr. Tangent of theta, that's not so terrible, because it's just negative square root of 2 divided by square root of 2, which is negative 1. So if you just rely on your calculator, this is going to tell you that theta is negative 45 degrees. That's incorrect. Well, the calculator is correct, but where is this? Well, I guess that is correct. We are in the fourth quadrant, aren't we? Go over 2, down 2. We're in the fourth quadrant. So we can use that. Theta equals negative 45 degrees. So in polar form, this is going to be 2 CIS negative 45. Ooh, this other one's almost in the exact same spot. This one, Z2 in polar form. Bueller. R equals square root of 2. All right, good. And what about tangent of theta? That's also going to be negative 1. So here theta equals negative 45 degrees. So in polar form, this little guy is going to be square root of 2 CIS negative 45 degrees. Now I'm going to make a suggestion here that you ought to follow. I'm going to change each of these into this. What am I doing here? Is there any difference between negative 45 degrees and 315 degrees? Nope. But there is going to be a big difference once we start using these formulas. You'll see what I mean here in just a second. Sometimes. Here it wouldn't have made a big deal, but I'm going to put them as positive angle measures. Now we can do part A and part B. So for part A, the product of two complex numbers is the product of their R values. So Z1 times Z2 is going to equal R1 times R2, which is 2 root 2. And then you have to add the two angle measures. 315 plus 315 is 630. That's once around a circle plus how much more? Now, unless the directions specifically say write it in standard form, just leave it in polar form. What do the directions here say? No directions. All right. Well, we'll leave it in polar form then. Bless you.
Thank you.
Now for part B, the quotient of these two is going to be the quotient of the two R values, R1 divided by R2. Oh, man, that's going to give us a square in the denominator. That's no good. And we're going to have to mess with that here in a second, but just to write this out before we mess with, we can't leave it like that, but anyway, what's going to be our argument here for the angle measure? Yeah, you subtract the 2, so it's going to be 0. All right, what is 2 divided by square root 2? Got times top and bottom by square root 2, so it's 2 root 2 over 2. And then the 2's cancel. So that's just the square root of 2. CIS 0 degrees. Okay, we're only about halfway done with this. We still need to do Dommage's theorem. What else did I have in there? Dommage's theorem and something else. Oh, that's going to take forever. That's a whole nother lesson in and of itself. So, all right, well, Wednesday we're going to have to finish up these two right here. Dommage's theorem and the nth roots of complex numbers. Just to give you a little preview, the bell's going to ring here in about 2 minutes. We've got time. But the nth root of complex numbers. Oh, what's a good way to just to give you a preview here? This, for example. How many square roots of 9 are there? Technically, there's 2, right? What are the 2 square roots of 9? Plus or minus 3, right? Now, this never really ever comes up in Algebra 2 because it's way beyond the scope of Algebra 2, but how many cube roots are there of 27?
1.
There's 3 cube roots of 27. We know one of the real ones. What's the real cube root of 27? 3, but there's 2 others that are complex. It's along those same lines, but we don't know the other 2 roots, cube roots of 27 yet. We have to use this theorem, the nth roots of complex numbers. But you understand what I'm talking about? The number of roots of a number has to equal the index of that root. If it's a cube root of 27, there has to be 3 cube roots of 27. We only know how to find one of them right now. We have to learn how to find the other 2. Or this one. How would you answer this question? But that's only one of the fourth roots. How many fourth roots of 16 are there supposed to be? There's supposed to be 4 fourth roots. That's only one of them. There's 3 others. Another one's -2, but then there's 2 others that are complex. So that's what that is all about. So anyway.